When you look up into the night sky, have you ever wondered if the universe itself might have a rhythm? A kind of breathing, slow and steady, hidden within the vastness of stars? Astronomers have found that at the very heart of many galaxies, there exists something invisible and immensely powerful. It is not a star nor a cluster of them, but rather a deep well in the fabric of space, a supermassive black hole. To many the phrase may sound frightening, like a monster that swallows everything nearby. Yet if we sit with the idea more calmly, we find that black holes are not merely destroyers. They are regulators, caretakers in their own way, helping galaxies maintain balance much as lungs regulate breath or a heart regulates flow. Imagine a galaxy as a living system. It has growth, it has circulation, and it has limits. In its centre, the black hole acts as a kind of governor, releasing streams of energy and matter that ripple outward. These jets, though invisible to the naked eye, can heat surrounding gas, slowing down the formation of too many stars, preventing a galaxy from burning itself out too quickly. Without this regulation, galaxies might swell uncontrollably and collapse into lifeless collections of exhausted suns, what scientists sometimes call zombie galaxies. It is an odd thought, isn't it? That something born of collapse, of gravity so strong it allows no escape, could be the very thing that keeps a galaxy alive. It is as though within darkness there is not only an end, but also a rhythm that sustains. Tonight, we begin a journey into this hidden world. We will move slowly, step by step, through what scientists have discovered about black holes, where they come from, how they shape galaxies, and why even their quiet presence is vital to the cosmic balance. And as we wander deeper, we will pause often, to reflect, to wonder, and to rest with the knowledge that even the most mysterious parts of the universe are not beyond our reach. To understand these mysterious giants, we must first ask, what exactly is a supermassive black hole? At its simplest, it is a region of space where gravity has become so strong that nothing, not even light, can escape once it crosses a certain invisible boundary. This boundary is called the event horizon. Beyond it, the rules we know no longer apply. Time and space are pulled inward, and even the fastest particle cannot turn back. But let us not rush. Imagine standing on the edge of a very deep well. If you lean too far and slip, gravity will draw you downward. The deeper the well, the harder it is to climb back. A black hole is like a well without a bottom, where the walls are so steep that even light cannot climb out. Yet, despite their fearsome reputation, black holes are not cosmic vacuum cleaners. They do not roam the galaxy, sucking in everything they pass. Their gravity behaves like that of any other massive object. A star or a planet orbiting at a safe distance will continue circling peacefully, just as the Earth circles the Sun. To fall in, an object must come very close, crossing that invisible edge where escape is no longer possible. It helps to think of them not as monsters, but as anchors. They hold galaxies together, shaping the dance of stars, influencing the cycles of birth and death within cosmic neighbourhoods. And in their centres they carry a mystery. How can something so small in volume hold the mass of millions, or even billions of suns? The truth is, black holes come in many sizes. Some are born when massive stars reach the end of their lives. After burning through their fuel, these stars collapse under their own weight, leaving behind a dense remnant. If the remnant is heavy enough, usually more than a few times the mass of our Sun, it forms a stellar mass black hole. But supermassive black holes, the kind that rest in galactic centres, are of a different order. They weigh not a few suns, but millions or billions. How such giants first formed is still one of astronomy's greatest questions. Were they seeded in the early universe by the collapse of enormous clouds of gas, skipping the stage of being stars at all? Or did they grow slowly, feeding for billions of years, merging with other black holes along the way? Scientists suspect both stories may be true, depending on where and when we look, and in that uncertainty we find the beauty of discovery. The universe still keeps many of its secrets close. So we begin with this picture, black holes as quiet anchors, their pull shaping the galaxies we see. But before we can know how they grow, we must step back into history, when the very idea of a black hole was not yet proven, but only written on paper. Long before we could take pictures of galaxies, or even dream of telescopes that could peer across billions of light years, the idea of a black hole was born quietly, on paper. In 1915, Albert Einstein introduced his theory of general relativity. It was a new way of understanding gravity, not as a force pulling at objects, but as the bending and shaping of space and time itself. The following year, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations. His mathematics revealed something almost unbelievable. If enough mass were concentrated into a small region, space-time would curve so steeply that nothing could escape. At the time, it was treated as a mathematical curiosity. Even Einstein himself doubted whether nature would allow such an object to exist. For decades, the idea of a black hole remained mostly theory, a strange possibility hidden within the equations of relativity. But the universe had already written these objects into its design, and slowly evidence began to arrive. In 1964, astronomers studying the constellation of Cygnus discovered a powerful source of X-rays. It was unlike ordinary stars, too intense to be explained by normal processes. They named it Cygnus X1. Careful study revealed what was happening. Material from a companion star was falling into an unseen massive object. As the material spiraled inward, it heated up to millions of degrees, glowing in X-rays before vanishing beyond a boundary. For the first time, we had strong evidence that black holes were not just theory, they were real. They existed in our galaxy. And they had a way of showing themselves not by being seen directly, but by how they influenced their surroundings. This was the beginning of a quiet revolution in astronomy. We could no longer think of black holes as mere curiosities. They were part of the cosmos, as real as stars and planets. Today, when we imagine a black hole, we often picture it as a dark sphere surrounded by glowing light. But the truth is more subtle. Black holes cannot be seen directly. What we see is the effect of their gravity on nearby matter. We see the glowing disk of gas and dust spiraling inward. We see jets of particles shooting out along their poles, and in some cases we see stars whipping around an invisible centre, moving so fast that only a hidden giant could explain their speed. There is humility in this story. The greatest mysteries of the universe are often invisible to us. We learn about them not by direct sight, but by watching how they touch everything else. And so, with patience and persistence, scientists began to uncover the structure of a black hole, not in myths or guesses, but in careful layers of understanding. To picture a black hole, we must think in layers, quiet, invisible layers that define what can and cannot happen near its edge. The first of these is the event horizon. This is the invisible boundary surrounding the black hole. Once something crosses it, whether it is a particle of light, a star, or even time itself, it cannot return. To the outside universe, whatever falls in is gone. The horizon marks the point of no return. Yet from afar it is not a wall, nor a barrier we could ever touch. It is only a place in space where escape becomes impossible. Just beyond the event horizon lies another strange region, the photon sphere. Here, light itself is caught in a fragile balance. Photons can orbit the black hole in circles, racing endlessly around it, though in practice such orbits are unstable. A small nudge inward, and they vanish into the hole. A nudge outward, and they escape into the wider universe. Imagine light, the fastest thing we know, reduced to a captive dancer, circling endlessly until chance decides its fate. At the very centre lies the singularity. It is a point where our physics falters, where density becomes infinite, and our equations no longer describe reality. We do not yet know what truly happens there. It is not so much a place as it is a mystery, a signpost reminding us that science, no matter how far it has travelled, still has edges. Together these three parts, the event horizon, the photon sphere, the singularity, create the structure of a black hole. Though we cannot see them directly, we infer their presence through observation, through theory, and through the behaviour of the universe itself. And black holes themselves are not all alike. They come in a range of sizes. Stellar mass black holes form from the collapse of massive stars, their weight usually a few to a dozen times greater than our Sun. Intermediate black holes sit between stellar and supermassive, ranging from hundreds to hundreds of thousands of solar masses, though they are rare and difficult to confirm. Finally, the giants, the supermassive black holes, weigh millions, even billions of suns. These are the ones that rest at the hearts of galaxies, shaping their evolution quietly over cosmic time. In 2019, humanity caught its first true glimpse of one of these titans. The Event Horizon Telescope, a network of radio observatories spread across Earth, combined their data to form a planet-sized virtual telescope. The result was the first direct image of a black hole's shadow, resting at the centre of the galaxy M87. The dark circle, surrounded by a glowing ring of light, confirmed what theory had long suggested. It was as though the universe had opened a window, letting us glimpse something we had only imagined. That moment was a milestone, not because the mystery was solved, but because the unseen was now seen, the imagined made real. And so, as we move deeper, we begin to ask not only what black holes are, but what role they play in the larger story of galaxies and of the universe itself. One of the questions that lingers gently in the background is this: do black holes ever die? For much of modern astronomy, black holes were seen as eternal, silent anchors in the cosmos. Yet in the 1970s, Stephen Hawking proposed a new idea, one that added both mystery and fragility to their nature. He showed that black holes might slowly lose mass, not through anything falling in, but through a faint radiation now called Hawking radiation. Here's how it works, in the simplest terms. Space is never truly empty. Even in the quietest vacuum, tiny pairs of particles flicker in and out of existence. Normally they appear together and quickly vanish again. But near the event horizon of a black hole, something unusual can happen. One particle falls inward, while the other escapes outward. From the perspective of the wider universe, it looks as if the black hole has lost a tiny piece of itself. Over unimaginably long time scales, trillions upon trillions of years, this process could allow a black hole to slowly shrink and eventually vanish. To us, living on human scales, this is not something we will ever witness. A supermassive black hole will outlive every star we see in the night sky. But the idea itself softens the notion of black holes as eternal prisons. Even they, it seems, may not last forever. For now, though, they remain abundant. Astronomers estimate that in our galaxy alone, there may be over 100 million black holes of various sizes. Most are quiet, hidden, and difficult to detect, revealed only when a nearby star betrays their presence. But at the very heart of our own Milky Way, we know of a giant, Sagittarius A. It sits about 26,000 light-years from Earth, with a mass equal to about 4 million suns. From Earth, we cannot see it directly with our eyes. Dust and gas obscure the centre of our galaxy. Yet by tracking the paths of stars whipping around an invisible point, scientists have measured its presence with remarkable precision. Those stars move so quickly, in such tight orbits, that only a supermassive black hole could explain their speed. There is something strangely reassuring in this. We live in a galaxy with a giant heart, one that beats not in light, but in gravity. It anchors us, it stabilizes the grand spiral of the Milky Way, and it has done so for billions of years. And while Sagittarius A is calm now, gently feeding on sparse material, there were times in the past when it likely shone as a bright, active core. Perhaps in the far future it will awaken again. For now, though, it rests, and we circle quietly around it, without ever noticing its pull in our daily lives. So we see, black holes are not distant curiosities. They are part of our own story, shaping the home we live in. If we wish to know these hidden giants better, we must learn how to weigh them. But how does one measure something that cannot be seen? Astronomers do this by watching the things that move around them. Stars orbiting near a black hole become like messengers, their motions tracing out the invisible mass they circle. By carefully recording their speeds and their paths, scientists can calculate the weight of the object at the center. This method has revealed extraordinary truths. Around Sagittarius A, the stars closest to the black hole whip through their orbits in mere years, rather than the centuries or millennia it would take at such distances if the mass were ordinary. Their speed is a signature, telling us the central object is millions of times heavier than our Sun, compressed into a space no larger than our solar system. Elsewhere, in other galaxies, similar techniques have uncovered even larger monsters. Some black holes weigh tens of millions, even billions of suns. One in the galaxy Centaurus A has a mass of 55 million suns. Another, in the cluster Abell 2261, may reach 100 billion. Such numbers are hard to hold in the mind. They remind us that the universe often works on scales far beyond our everyday imagination. And yet, even in their enormity, these black holes behave according to rules we can follow. The more mass they contain, the larger their event horizons, the slower the motions of their surrounding gas. By measuring the glowing disks of matter spiraling into them, astronomers can refine their estimates further. Each observation adds another quiet piece to the puzzle. Perhaps the most striking example came in 2019, when the Event Horizon Telescope unveiled the shadow of the black hole in galaxy M87. That dark circle, surrounded by a ring of light, was more than an image, it was a confirmation. For decades, theory had described what such a silhouette should look like. Now the universe itself had shown it to us. In that ring of light, bent by gravity into a halo, we saw not only the black hole, but the fabric of space itself being curved and shaped. It was, in a sense, a photograph of gravity at work. And as more such images emerge, we continue to refine our understanding. We learn not just how heavy these black holes are, but how they spin, how they interact with their surroundings, and how their presence ripples outward into the galaxies that host them. The act of weighing, then, is more than measurement. It is listening to the heartbeat of galaxies, through the motions of stars and the glow of falling gas. It is finding shape in the unseen, order in the invisible, and slowly we begin to glimpse not just what black holes are, but how they help set the rhythm for the cosmos itself. When we think of black holes, we often imagine them as dark voids, swallowing matter without end. But there is another side to their story, one filled with light, energy, and motion. Around many black holes, especially the supermassive ones at galactic centers, lies a disk of gas and dust. As material spirals inward, it heats to extraordinary temperatures, glowing brightly in X-rays and visible light. These glowing structures are called accretion disks. Far from being silent, they shine so intensely that they can sometimes outshine the entire galaxy in which they reside. Alongside these disks, many black holes produce jets, narrow beams of particles launched outward at nearly the speed of light. These jets can stretch across thousands of light years, piercing through the interstellar medium, influencing the galaxy around them. For us on Earth, they look like glowing lances of energy captured in radio waves and high-energy radiation. At first glance, these processes might seem destructive, heating gas, expelling matter, disrupting star formation. But in truth, they are part of a delicate balance. The energy released prevents galaxies from forming stars too quickly, from consuming all their available gas at once. In this way, black holes help set the pace, ensuring galaxies evolve over billions of years instead of burning out in cosmic youth. It is tempting to think of this in biological terms. Just as our breathing regulates the flow of oxygen in our bodies, black holes regulate the breathing of galaxies. The push and pull of inflows and outflows, of matter drawn inward and energy pushed outward, sustains the long-term health of cosmic systems. And what of their origins? How did these supermassive black holes grow so vast, so early in cosmic history? This remains one of astronomy's great puzzles. Some evidence suggests that enormous clouds of gas in the young universe collapsed directly into black holes, skipping the stage of becoming stars. These seed black holes may have grown quickly, feeding on their surroundings and merging with others. Others may have started smaller, as the remnants of early stars slowly building mass through steady accretion and galactic mergers. The truth is likely a blend of these pathways. The universe, as always, may have chosen more than one route. What is remarkable is that within the first billion years after the Big Bang, an eye blink in cosmic time, we already see quasars powered by black holes billions of times heavier than our Sun. Their growth must have been rapid, almost impatient, compared to the gentle pace of galaxies today. To imagine this is to picture a universe in its youth, still turbulent and hot, where the seeds of the structures we now see were already being planted. And as we reflect on this, we realize black holes are not simply the end of stars, they're also beginnings. They shape the galaxies that follow. They set the tempo of cosmic evolution. When galaxies drift through the universe, they do not always remain solitary. Over long timescales, they meet, approach, and merge, drawn together by gravity in a slow dance. When this happens, their stars largely pass by one another unharmed, for the spaces between stars are vast. But at their centres, something more dramatic unfolds. Each galaxy carries its own supermassive black hole, and as the galaxies merge, the black holes are drawn toward each other. They spiral inward, tracing great arcs, slowly closing the distance between them. At first, their presence stirs the gas and dust in their surroundings. Material is funneled toward them, igniting bursts of star formation and powering luminous accretion disks. The galaxy becomes active, glowing across the spectrum. Then, as the black holes approach closer, their gravitational pull begins to dominate the region, shaping the motions of stars and clouds on scales far greater than our minds can comfortably hold. Eventually they merge. Two singularities become one, releasing a final powerful surge of energy. Some of this energy emerges as intense jets of particles, brighter and stronger than those produced by isolated black holes. Some is released as gravitational waves, ripples in the very fabric of space-time, spreading outward across the cosmos. These waves are subtle. By the time they reach us billions of light-years away, they are softer than the width of an atom. Yet our instruments can detect them. Each wave is a message from the distant past, telling of a merger that once shook the universe itself. The future holds even greater possibilities. Projects like the Laser Interferometer Space Antenna, LISA, a planned collaboration between NASA and the European Space Agency, will one day orbit the Sun, sensitive enough to detect gravitational waves from supermassive black hole mergers across the universe. When combined with telescopes that capture light, radio waves, and X-rays, these detections will give us a complete picture. Both the light we see and the vibrations of space we cannot. These mergers are not just violent ends, they're also beginnings. The new black hole that forms often becomes the heart of a larger reshaped galaxy. Out of collision comes structure, out of turbulence comes balance. It is humbling to think that galaxies, including our own, may have grown through such encounters. That the stars we see tonight, stretched across the Milky Way, exist in part because long ago our galaxy was shaped by such cosmic unions. Mergers remind us that the universe is not static. It is not a frozen tableau of stars. It is alive, always moving, always changing, and in its heartbeats of billions of years, black holes play a quiet, steady role. In recent years, astronomers have found new ways to study these giants more closely. One of the most delicate methods involves listening not to their gravity, but to their light. At the centre of our own galaxy, Sagittarius A, scientists have observed something remarkable: polarized light. To explain it gently, light waves can vibrate in many directions, but when they pass through magnetic fields, their orientation can become ordered or polarized. By studying this pattern, astronomers can map the invisible structure of magnetic fields around a black hole. This discovery was striking. The magnetic field around Sagittarius A turned out to be surprisingly organized, resembling those found around the much larger black hole in the M87 galaxy. Despite their enormous difference in size, M87's black hole is more than 1,000 times heavier. The patterns were familiar. It is as though black holes, no matter their scale, follow the same quiet blueprint. Ordered magnetic fields may be a universal feature, guiding how material falls in, and perhaps driving the mysterious jets that so many of them produce. What makes this even more intriguing is that Sagittarius A looks calm to us. It does not produce the spectacular blazing jets that some black holes unleash. Yet its magnetic structure suggests that such a jet might exist, hidden or faint, waiting for the right moment to reveal itself. The Event Horizon Telescope, the same project that captured the first image of M87's black hole, played a key role in this discovery. By combining data from observatories across the world, scientists created a virtual telescope as large as Earth itself. Only with such power could we resolve the swirling gas so close to the black hole and glimpse the patterns imprinted upon it. There is humility in this. Even when studying the closest supermassive black hole we know, only 26,000 light-years away, we struggle to see clearly. Dust clouds, rapid gas motions, and the small size of Sagittarius A make it difficult to capture sharp images. In comparison, M87's black hole is larger, its material moving more slowly, giving us a steadier view. Yet even blurred glimpses are enough to tell us that order exists where we expected chaos. That magnetic fields, invisible and delicate, may be the unseen architects shaping how black holes interact with their galaxies, and so, as we trace these patterns of light and magnetism, we find not only answers but new questions. Could the magnetic fields of Sagittarius A be whispering of a hidden jet? Could such a quiet giant, resting in the centre of our Milky Way, one day flare into brightness? For now, it waits. And we watch patiently, knowing that even in stillness, black holes are at work, shaping their environments in ways we are only beginning to understand. Magnetic fields, though unseen, may be among the most important features of black holes. They act like invisible threads, guiding the motion of gas, controlling the formation of jets, and shaping how energy escapes into the wider galaxy. Think of them as scaffolding, delicate invisible frameworks that hold together the processes we cannot otherwise explain. Without magnetic fields, much of what we see near black holes would remain a mystery. Why matter forms stable disks instead of collapsing immediately? Why some black holes remain quiet while others burst with energy? Why jets can remain focused across thousands of light-years instead of dispersing quickly into space? The discovery that Sagittarius A and M87's black hole share similar magnetic patterns suggests something profound. That this ordered structure might be universal. No matter the scale, whether a few million or several billion times the mass of our Sun, the same principles seem to apply. Black holes may differ in size, but their behaviour follows familiar rules. If this is true, it opens a new path in our understanding. By studying the most distant and powerful active black holes, we may learn something about our own, closer one. And by studying Sagittarius A, hidden in the heart of our galaxy, we can refine our models for those farther away. Some scientists even speculate that Sagittarius A might harbour a faint jet, too subtle to see clearly yet, but present nonetheless. Jets require magnetic fields to remain focused, and the patterns we observe around Sagittarius A suggest the conditions are right. If such a jet exists, it could link our galaxy's centre more directly to the processes that regulate star formation and galactic evolution. The idea is not without wonder. We often think of our Milky Way as calm, a spiral drifting quietly among billions of galaxies. But at its centre lies a giant with hidden power, perhaps not sleeping, only resting. It is through instruments like the Event Horizon Telescope, a collaboration that links observatories across the globe, that we can uncover such truths. By combining data into one Earth-sized eye, we create images of black holes with unprecedented clarity. Each new observation peels back another layer of mystery. Even so, our work is not finished. To see clearly around Sagittarius A, astronomers must overcome the challenge of turbulence, dust, and rapid gas motion. The closer we look, the faster the material moves. The black hole is small compared to M87's, making it harder to capture steady images. Yet these very challenges make the discoveries more rewarding. Magnetic fields remind us of something deeper, that nature often hides its order behind apparent chaos. In the swirl of matter, in the bending of light, in the shadow of a black hole, there is structure, and if we listen carefully, we may begin to hear the quiet universal patterns that bind galaxies together. When we look beyond our own galaxy, we see countless others, each with a black hole of its own at the centre, and with each one, the story becomes richer. Some are quiet, as ours is today. Others blaze with energy, their jets and disks shining brighter than all the stars around them combined. One galaxy, known as the Teacup Galaxy, offers a vivid example. It lies more than 1 billion light-years away, and at its centre lives a supermassive black hole. Though not among the brightest or most powerful, it has shaped its environment in a remarkable way. Astronomers gave the galaxy its nickname because of a striking feature, a loop of glowing gas like the handle of a teacup. This structure was sculpted by the activity of the central black hole. Its jets, though relatively weak compared to some, created bubbles of energy that pushed into the surrounding gas, heating and disturbing it. The result is a cosmic sculpture that has endured for millions of years. The lesson of the Teacup Galaxy is simple. Black holes do not need to be violently active to change their surroundings. Even modest activity, jets that are less intense, bursts that are shorter, can move and heat gas, disrupting how stars are formed. The effect ripples outward, influencing not only the heart of the galaxy, but its broader evolution. Recent observations with the Atacama Large Millimeter Array in Chile revealed that the black hole's jets were not only pushing gas outward along their path, but also stirring the gas sideways. Shock waves from the bubbles spread perpendicular to the jets, compressing and heating material in unexpected directions. This sideways stirring might sound minor, but it changes everything. Gas that could have cooled and condensed into stars remains too hot. Star formation slows or shifts to other regions. Over long stretches of cosmic time, the galaxy's growth is shaped, its starry future rewritten, all because of a black hole at the centre, releasing just enough energy to keep balance. There is a gentle paradox here. Black holes grow by pulling matter inward, yet they preserve galaxies by pushing energy outward. They are not simply destroyers, nor are they simple givers. They are regulators, both feeding and restraining, both consuming and protecting. And in this paradox lies a kind of harmony. Just as our own breath has two parts, inhalation and exhalation, so too do galaxies breathe through their black holes. Matter falls in, energy flows out, and across billions of years, that rhythm maintains the health of galaxies. It is easy to forget that the vast spirals and ellipses of galaxies we see today are not accidents. They are the products of regulation, of balance, of cycles that unfold slowly and invisibly. And though black holes themselves remain hidden, their influence is written in the stars that do and do not form around them. As we reflect on these cosmic rhythms, it becomes clear that black holes are not exceptions to the universe, but part of its order. They remind us that creation and destruction are often intertwined, that balance is maintained not by silence, but by gentle regulation. In galaxies like the Teacup, we see how feedback from black holes prevents runaway growth. Without it, vast clouds of gas might collapse all at once, forming stars too quickly and too many. The galaxy would burn brightly for a short time, then fade, exhausted, its fuel spent. Instead, black holes slow this process, heating and stirring the gas, keeping star formation steady across billions of years. Astronomers call this negative feedback, yet the name hides its elegance. It is not a punishment, but a safeguard. It ensures that galaxies live longer, that stars and planets can form at a pace that allows complexity to emerge. Without this restraint, the universe might look very different. Briefer flashes of light, fewer stable worlds, perhaps less time for life to arise. The comparison to breathing is once again useful. When we breathe, our diaphragm contracts and relaxes, allowing air to enter and leave our lungs. This rhythm sustains us, balances oxygen and carbon dioxide, and keeps our body alive. In the same way, the outflows from black holes act like a galactic diaphragm. They regulate the air of the galaxy, its gas, ensuring that it neither collapses too quickly nor stagnates unused. It is a quiet process. We do not see it in a single moment. It takes millions, even billions of years for the effects to become clear. Yet patience reveals the pattern. Galaxies shaped not only by the stars they birth, but by the hidden regulators at their core. Even now, computer simulations show us these processes in motion. Astronomers model galaxies with and without black hole feedback, and the results are striking. Without black holes, galaxies become bloated, dense, and short-lived. With them, galaxies breathe. They cycle through growth and rest, expansion and calm. They resemble the living systems we know, not in detail, but in rhythm. Perhaps this is why the idea of a heartbeat in the universe feels so natural. We sense patterns of balance in our own lives. Inhale, exhale, day, night, birth, death. It is not surprising that, when we look outward, we see echoes of these rhythms on cosmic scales. The black holes remind us of this balance. Silent, invisible, patient, yet always present, shaping the galaxies we see. And now, having traced their role as regulators, we turn to another question. If black holes are so central, then what can they teach us about the universe's deepest mysteries, about life, order, and complexity itself? The universe often invites us to see patterns where none seem obvious. Stars live and die, galaxies grow and fade, and somewhere in the quiet between, life arises. But how do we measure something as subtle as complexity? How do we know when the random becomes ordered, when the simple becomes alive? This is where a new idea, known as assembly theory, offers a perspective. It suggests that complexity can be measured in steps, like counting how many pieces it takes to build a puzzle. The more steps required to construct a structure, the more unlikely it is to appear by chance. Imagine you are stacking blocks. A single block is simple. It could appear almost anywhere. 2 blocks together are still easy. But as the tower grows taller and more intricate, the odds of it forming randomly shrink. At some point, the arrangement begins to tell a story. It holds memory. It shows that a process guided its growth. In this way, assembly theory treats life not just as a biological phenomenon, but as a measure of complexity itself. From atoms to molecules, from proteins to cells, each step is an increase in the assembly index, the count of how many building steps were needed. This idea connects surprisingly well with physics. The Standard Model describes the fundamental particles and forces that make up the universe. On its own, it explains the raw materials of reality. But assembly theory goes further, describing how these raw materials combine, step by step, into the structures we see in biology. The concept of a state space is useful here. It is like a map of all possible configurations matter can take. Life, then, is a path through this map, a journey across branching routes, where each step builds greater complexity. Some paths lead to dead ends. Others continue, branching further, until molecules become self-replicating, until cells arise, until ecosystems flourish. Seen this way, evolution itself is not only biology, but mathematics unfolding. Complexity is not random, it is structured growth, guided by physics, but enriched by history. And what does this mean for the question so often whispered beneath the stars? Are we alone? If complexity can be measured, then perhaps it can also be detected. Assembly theory suggests a new way to search for life beyond Earth. Instead of scanning for radio signals or looking for oxygen in an atmosphere, we might measure the complexity of the molecules found elsewhere. If they are too intricate to have formed by chance, then they may point to processes akin to life. Picture a spacecraft sampling the atmosphere of a distant exoplanet, or the icy surface of a moon like Europa or Enceladus. Within its data, scientists might find molecules with a high assembly index, structures unlikely to arise in lifeless chemistry. Such a discovery would not be proof, but it would be a powerful hint that life's patterns extend beyond Earth. Of course, challenges remain. Our definition of a life is grounded in what we know here. An alien life might follow rules we cannot yet imagine. The universe is vast and our instruments still limited. But the idea that complexity itself can serve as a signature opens a new door. In the gentle rhythm of assembly, we begin to see how the cosmos might weave life into its fabric, not as a rare accident, but as a possible outcome of matter's endless dance. To think about life in terms of complexity is to return, again, to one of nature's oldest companions, entropy. Entropy is the measure of disorder, of how systems tend to spread into randomness. Left alone, a deck of cards becomes shuffled, not ordered. Heat spreads, never gathers itself back without help. Yet life seems to do the opposite. From the raw materials of Earth, it created order. Molecules into cells, cells into organisms, organisms into ecosystems. At first glance, this appears to defy entropy. But in truth, life does not break the rules. It works within them. By taking in energy, by building structures while shedding heat, life creates local order, even as the universe as a whole still trends toward greater disorder. Assembly theory frames this as a quiet victory. Each step of molecular building is a triumph over entropy, a careful stacking of pieces into patterns that persist. With every increase in complexity, life demonstrates its ability to move against the tide even while respecting it. Imagine the early Earth, a world of oceans and storms, of volcanic heat and chemical soup. Within that mixture, molecules combined and recombined endlessly. Most arrangements dissolved as quickly as they formed, but a few managed to hold together, to persist, to remember their shape. These molecules stored information. They copied themselves, imperfectly but sufficiently. And with each cycle, complexity grew. This, perhaps, is where memory entered the story of life. Not the memory of minds, but the memory of molecules, chemical structures capable of keeping a record of themselves, of passing on their form through replication. From this, the first fragile strands of life's story were written. Assembly theory calls attention to this process. Each replication, each step toward greater intricacy, raises the assembly index. The chance that such complexity could emerge by accident alone becomes smaller and smaller. At some point, we cross from randomness into pattern, from chemistry into biology. It is humbling to think of evolution in this way, not only as survival and adaptation, but as the slow climb of complexity across the landscape of possibilities. Each branch on the tree of life is a new path taken in this mathematical journey. And this perspective gives us a new tool in the search for life beyond Earth. If we can measure the complexity of molecules elsewhere, on Mars, in the atmosphere of an exoplanet, in the icy plumes of Saturn's moon Enceladus, we may detect the fingerprints of life, not by resemblance to Earth, but by the sheer improbability of such patterns forming without guidance. Of course, there are cautions. Life elsewhere may not follow the same chemistry. Its complexity may look different. Our instruments are still young, our reach limited. Yet the approach is promising. It allows us to ask not only, is there life, but also, how complex might it be? And perhaps most importantly, it ties us back to a deeper theme. Life, in this view, is not an anomaly against the universe. It is an expression of the universe's capacity to weave complexity out of simplicity, order out of chance. It is part of the same rhythm we see in galaxies and black holes, a balance between growth and restraint, between entropy and structure. Every molecule that remembers its form, in every star that regulates its galaxy, the cosmos reveals itself as a place of patterns, emerging slowly, patiently, over billions of years. The question of whether life exists elsewhere in the universe has followed humanity for as long as we have looked up at the stars. Assembly theory does not answer it directly, but it gives us a framework to ask in a new way. If life is a process of building complexity, then perhaps we can look for signs of that building wherever we can measure. Instead of searching only for familiar clues, like oxygen in an atmosphere or radio signals from distant civilizations, we might look for molecular fingerprints of unlikely complexity, patterns too intricate to be random, too structured to be the product of simple chemistry alone. Imagine a future probe sent to the oceans beneath Europa's icy shell. If its instruments found molecules with a high assembly index, structures that would be improbable without replication, we would have reason to pause. It would not be final proof, but it would whisper that life's story might not be confined to Earth. Or picture telescopes of the future studying the atmospheres of distant exoplanets. By breaking apart the faint light of a star as it passes through a planet's air, they could search not only for gases but for molecular patterns that hint at complexity. If found, those signatures would expand the question of life beyond speculation, grounding it in observable data. Yet the challenge remains enormous. Our instruments are delicate compared to the scale of the cosmos. The signals we can detect are faint, blurred by distance and filtered by noise. The universe is vast and our reach is still small. There is also a deeper uncertainty. Our definition of life is earth-bound. We know carbon-based chemistry, water as a solvent, DNA as a carrier of memory. But what if life elsewhere follows different paths? What if it builds complexity in ways that do not resemble our own? Assembly theory gives us a language for complexity itself, but even that may not capture every possibility. Still, the pursuit is meaningful. Even in its limitations, it draws us closer to the cosmos, reminding us that we are part of a greater pattern. To ask these questions is itself a reflection of complexity, a species able to wonder about its place, to measure, to seek answers. Science is by nature cautious. Every new theory must withstand criticism and debate. Assembly theory is no exception. Some researchers argue it oversimplifies, or that its definitions of complexity may not apply everywhere. Others see promise in its ability to connect chemistry, biology, and physics in one framework. But perhaps the value of such ideas lies not only in their correctness, but in the conversations they open. They remind us that science is not a finished book, but an ongoing dialogue between theory and observation, between evidence and imagination. And so, as we listen to the universe through black holes and through molecules, we begin to hear echoes of the same theme: balance, order, and rhythm emerging from apparent chaos. The universe, it seems, is not silent. It breathes, it remembers, it assembles. And in that slow unfolding it leaves traces we can follow if we learn to listen carefully enough. If life is complexity built step by step, then its story on Earth is one of patience. For billions of years, molecules combined and recombined, rising in complexity, guided by the quiet laws of physics and chemistry. At some point, the line was crossed. Replication began, memory was preserved, and evolution took hold. Assembly theory reminds us that each of these steps increase the improbability of randomness. The more intricate the structure, the less likely it is to appear by chance. Life, then, becomes a natural outcome of matter's tendency to explore the landscape of possibilities, carving out paths where order can persist. But life is not only about complexity, it is also about resilience. It survives in boiling vents at the ocean's floor, in the frozen deserts of Antarctica, in the thin air of mountain peaks, and even on the edge of space. If life can adapt to such extremes here, then perhaps elsewhere in the cosmos, under alien suns or beneath icy moons, it too may find a way. Assembly theory offers us a new lens to interpret such resilience. In every adaptation, in every structure preserved, complexity deepens. The assembly index climbs as life explores new configurations branching into endless forms. And yet, with every step forward, science itself is also tested. No theory exists in silence. Assembly theory has drawn both enthusiasm and skepticism. Some scientists see in it a profound bridge between physics and biology, a universal measure of complexity. Others caution that it may be too simplified. that life cannot be captured in numbers alone. This tension is not a weakness. It is the way science breathes. Ideas are proposed, tested, challenged, refined. In debate, we sharpen our understanding. In criticism, we find strength. Even disagreement is part of the process by which knowledge grows. The very act of questioning, of not accepting answers too quickly, mirrors the cautious rhythm of the universe itself. Just as galaxies grow slowly, regulated by their black holes, so too does our knowledge grow, regulated by skepticism and evidence. Perhaps that is the deeper lesson, that patience is woven into everything. Stars live for billions of years. Black holes shape galaxies over eons. Life crawls forward through countless generations before it blooms. And our science too unfolds step by step, never rushing, never final. So when we speak of assembly, whether of molecules, of galaxies, or of ideas, we are speaking of the same rhythm, a slow construction, a balance between chance and order, a patient unfolding of patterns across time. And as we hold this thought, we turn again to the stars, where endings also play their role in beginnings. For just as black holes regulate galaxies, so too do dying stars scatter the elements that make life possible. When a massive star reaches the end of its fuel, something extraordinary happens. Its core, once a steady furnace, begins to falter. Fusion slows and gravity, relentless and patient, takes over. The star collapses inward, then rebounds in a colossal explosion. This is a supernova, one of the most powerful events in the universe. For a brief moment, a single star can outshine its entire galaxy. Light floods across space, visible from millions of light years away. And yet, the brilliance of a supernova is not its only gift. It is also the universe's way of recycling. Within these explosions, elements heavier than hydrogen and helium are forged. Carbon, oxygen, silicon, iron, all of which are essential for planets, oceans, and life itself, are born in the furnace of dying stars. When the supernova releases them into space, they spread through the galaxy, enriching gas clouds, seeding future generations of stars and planets. Without supernova, there would be no Earth, no oceans, no soil, no living beings. We, quite literally, are the ashes of stars, arranged and reassembled by the patient hand of time. One star in particular has captured human imagination for centuries: Betelgeuse, the red supergiant in Orion's shoulder. Easily visible to the naked eye, it has long been a point of wonder. Recently, its sudden dimming and brightening sparked speculation that it might soon explode. But closer study revealed another story. Betelgeuse is enormous, about 700 times the size of our Sun, and highly unstable. Its brightness changes because of vast convective cells, waves of hot plasma rising and falling, and clouds of dust drifting across our view. These changes may look like warnings of an imminent explosion, but in truth, Betelgeuse may still live for tens of thousands, even hundreds of thousands of years before it reaches its final collapse. Still, when it does eventually die, the spectacle will be unforgettable. From Earth, it could shine as bright as the full moon, visible even in daylight. And though it lies hundreds of light years away, its supernova would be harmless to us, a distant but magnificent display of cosmic transformation. Supernovae, then, are not only endings but beginnings. They are the universe's way of creating the raw materials for new worlds and eventually new life. They show us that even destruction carries within it the seeds of renewal. And so the rhythm continues. Stars are born, they live, they die, and their remains enrich the cosmos. Galaxies breathe through their black holes. Molecules assemble step by step into life. Everywhere we look, the story is one of cycles, of endings feeding beginnings, of order rising quietly from chaos. To understand why stars like Betelgeuse must one day end in such brilliant fashion, we must look inside them, into the quiet layers of their cores. Stars live by fusion. In their centres, hydrogen atoms fuse into helium, releasing light and heat. This balance between the outward push of fusion and the inward pull of gravity keeps a star stable for most of its life. For a star like our Sun, this balance can last billions of years. But massive stars, far heavier than the Sun, live much faster lives. Their gravity presses their cores to such extremes that fusion races ahead, burning through fuel at a staggering pace. They move quickly through stages of fusion, hydrogen to helium, then helium to carbon, then onward to heavier elements like oxygen, silicon, and finally iron. Iron is where the chain stops. Unlike lighter elements, iron does not release energy when fused. Instead, it consumes it. The star reaches a dead end. No more fuel to push against gravity, no more pressure to balance the collapse. When this moment arrives, the core caves in within a fraction of a second. The collapse is so sudden, so violent, that the outer layers of the star rebound outward, creating a shock wave that tears the star apart. The result is a supernova, a flash brighter than entire galaxies, a beacon that can be seen across the universe. But the explosion is more than light, it is a forge. In those final moments, the immense pressure and heat create elements heavier than iron. Gold, uranium, and others that fill the periodic table's upper reaches. These too are scattered into the cosmos, carried away on expanding waves of gas and dust. For ancient astronomers, supernovae were omens, bright stars that appeared suddenly in the night sky, shining for months before fading, were recorded as guest stars in Chinese, Korean, and Arabic chronicles. The earliest confirmed record dates back to the year 185 CE, when a new light was seen for 8 months before disappearing. For them, it was a mystery. For us, it is a reminder of the continuity between human wonder and cosmic truth. Today, supernovae remain vital tools for astronomy. Some, known as type Ia supernovae, occur in binary systems when a white dwarf star explodes after pulling too much material from its companion. Because these explosions have nearly uniform brightness, astronomers use them as standard candles, yardsticks to measure the distances to galaxies. Through them, we discovered that the universe is not only expanding, but expanding faster and faster, driven by something we call dark energy. So supernovae are not only spectacular events, they are teachers. They reveal the life cycles of stars, they enrich the cosmos with the elements of life, and they help us measure the shape and fate of the universe itself. From the death of stars, we learn about the birth of worlds. From their explosions, we glimpse both our origins and our destiny. Among the most astonishing explosions in the universe are those tied to gamma-ray bursts. These bursts release more energy in a few seconds than our Sun will emit in its entire 10 billion-year life. They are brief, but they are among the brightest signals we can detect across the cosmos. Gamma-ray bursts, or GRBs, are thought to come from 2 main sources. The first occurs when a massive star collapses into a black hole, producing jets of radiation that, if aimed toward us, appear as an intense flash. The second happens when 2 neutron stars collide, their violent union sending both gravitational waves and gamma rays across space. Most GRBs are short, lasting only seconds, but their impact is enormous. If one were to occur close to Earth and point directly at us, its energy could disturb our atmosphere, stripping ozone and altering conditions for life. Thankfully, such events are rare nearby. In October of 2022, astronomers witnessed what became known as the brightest gamma-ray burst ever recorded. Catalogued as GRB 2071A, it originated about 2.4 billion light-years away. Though unimaginably distant, its energy was so intense that it briefly affected Earth's ionosphere, disrupting radio signals. Satellites detected its blinding radiation, some even overwhelmed by its intensity. For 7 minutes, this cosmic beacon dominated our instruments. The afterglow lingered for weeks, allowing scientists to study it across many wavelengths: X-rays, optical light, radio waves. They expected to find signatures of heavy elements forged in the collapse that created the burst. Yet to their surprise, those signals were faint. The explosion's brilliance did not match the expected chemical fingerprints. This puzzled astronomers. GRBs had long been linked to the creation of heavy elements like gold and platinum. But GRB 201009A suggested the story might be more complex. Perhaps not all bursts forged these elements, or perhaps the signals were hidden by the sheer glare of the event. What is clear is that gamma-ray bursts remain among the most mysterious of cosmic events. They remind us that even after decades of study, the universe continues to surprise us, offering puzzles we cannot yet solve. For us, though, they are safe reminders, distant fireworks seen across billions of light years. They show us the extremes of energy, the raw power of collapsing stars, the fragile balance between matter and light. And once again, in their violence, they are also creators. The energy they release stirs galaxies, moves gas, and enriches the cosmos. In their fleeting brilliance, they connect the life cycles of stars to the greater story of cosmic evolution. It is remarkable, isn't it, that from moments so brief, lessons so enduring can emerge. Gamma-ray bursts, though terrifying in their intensity, are only one part of the larger story of stellar death. To place them in context, we must look again at how stars live out their lives, and how those lives ripple outward into the cosmos. For a star like our Sun, the end will be gentle. Billions of years from now, it will swell into a red giant, shedding its outer layers to form a glowing planetary nebula. Its core will shrink into a white dwarf, a quiet ember slowly cooling over trillions of years. No explosion, no gamma-ray burst, just a soft fading of light. But for the massive stars, those many times heavier than the Sun, endings are more dramatic. They collapse violently, they explode, and in some cases they leave behind neutron stars or black holes. In rare alignments, their collapse channels energy into narrow jets, and if those jets point toward us, we witness a gamma-ray burst. These events, though deadly up close, become precious to science at great distances. By studying their light curves, the way their brightness rises and fades, we learn about the processes deep inside collapsing stars. By comparing their afterglows across wavelengths, we gain clues about the gas and dust of their host galaxies. By linking them to gravitational wave detections, we confirm that even the most violent mergers follow the predictions of relativity. The 2022 burst, GRB 201009A, reminded us of both the power and the mystery of these events. Its brilliance was unmatched, so bright that some detectors were momentarily blinded, and yet its chemical fingerprints were puzzling, raising questions about how heavy elements are truly made. Did this burst forge gold and platinum or not? The answer is still unfolding. In the months after, astronomers pointed the James Webb Space Telescope and other instruments at the fading afterglow. They searched for traces hidden beneath the glare, hoping to catch the signature of new elements. The work continues, a reminder that discovery is rarely a single moment, but a slow process of watching, waiting, and interpreting. These rare cosmic beacons serve another purpose. They let us probe the universe itself. Their light, travelling billions of years, passes through gas clouds, intergalactic dust, and magnetic fields. By analysing how that light is absorbed and scattered, scientists can map the structure of the cosmos along its path. Each burst in this way becomes not just an explosion, but a probe, a message carrying information about everything it crossed. And so, what begins as the death cry of a star becomes a tool for understanding the universe. Even destruction in this cosmic rhythm contributes to creation. The story of gamma-ray bursts, then, is not finished. Each new detection adds another piece, each afterglow another clue, and like the stars themselves, our understanding continues to evolve, patient and unhurried. When astronomers study a star like Betelgeuse, they are not only watching a single star, but peering into the broader story of stellar evolution. Its changes in brightness, its vast convection cells, and its drifting clouds of dust are all part of the rhythm of a star nearing the later stages of its life. In 2019 and 2020, Betelgeuse dimmed so dramatically that some thought its final explosion might be imminent. For months it glowed faintly, its once familiar presence in Orion seeming to fade. But careful study showed that it was not the end. Instead, the dimming was caused by a massive cloud of dust formed when the star expelled part of its outer layers. This dust temporarily blocked our view until it drifted away. Betelgeuse, then, is not yet finished. Its core still fuses elements layer by layer in cycles that could last many thousands of years. But eventually, like all massive stars, it will reach the point of iron in its core, and gravity will win. The path it follows is familiar to astronomers. Stars of its mass enter cycles of pulsation, swelling and shrinking as their outer layers respond to changes in pressure and temperature. These pulsations can take hundreds or even thousands of days, rhythms so slow that they are imperceptible to us in the moment but clear when measured over years. In Betelgeuse, cycles of about 400 days and 2,000 days have been detected. Quiet heartbeats of a star preparing for its final act. When the end does come, the result will be spectacular. The explosion will cast iron, nickel, and heavier elements into space, enriching the interstellar medium. Its core may collapse into a neutron star, or perhaps, if heavy enough, a black hole. The light from its supernova will brighten our skies for weeks, perhaps even months. A reminder that stars are both creators and destroyers. For humanity, such an event would be safe. At its distance, roughly 600 light-years, it poses no danger. Instead, it would be a rare chance to witness a nearby supernova with our own eyes. Our ancestors recorded distant supernovae as mysterious guest stars. We would see Betelgeuse's end not as myth, but as science and as wonder. Supernovae like Betelgeuse's future one remind us that the universe is a cycle of renewal. The elements scattered by one star will seed the birth of new stars, new planets, perhaps even new life. In that way, endings are never truly endings. They are transitions, steps in the assembly of the cosmos. And as we reflect on this, we realize that the atoms in our own bodies, carbon, calcium, iron, were once forged in stars long gone. We carry within us the memory of supernovae, written into our bones and blood. So when Betelgeuse eventually fades in one last burst of light, it will not only be the end of a star, it will also be a continuation of a rhythm that has shaped the universe for billions of years. To understand what will eventually happen to Betelgeuse, and to stars like it, we must look more closely at the layers within a massive star. They're arranged almost like the rings of an onion, each layer fusing a heavier element than the one before. At first, hydrogen fuses into helium, as in our Sun. Later, helium becomes carbon, then oxygen, and so forth. Each stage is shorter than the last. Hydrogen fusion can last millions of years, but when a star reaches iron, the process ends in an instant. Iron cannot release energy through fusion. When it fills the star's core, fusion stops. Without outward pressure to resist gravity, the core collapses. Temperatures spike to billions of degrees, and in that fleeting moment shock waves erupt, tearing the star apart in a supernova. It is in these fiery deaths that the heaviest elements are made. Gold, silver, uranium, elements that shape worlds and lives, are created in the chaos of collapse and explosion. Without these events, the universe would be made almost entirely of hydrogen and helium. There would be no planets like Earth, no oceans, no life. For centuries, humanity has noticed these rare explosions. Ancient Chinese records describe guest stars that suddenly appeared in the sky, some lasting for months before fading. One of the most famous, observed in 1054 CE, became what we now call the Crab Nebula, a glowing cloud of gas and dust still visible through telescopes today. In its heart spins a pulsar, the remnant of the collapsed star ticking like a cosmic lighthouse. Supernovae are not only spectacles but also tools for science. Type Ia supernovae, the explosions of white dwarfs in binary systems, are especially important. Because they occur with nearly the same brightness each time, they act as cosmic mile markers. By comparing their known luminosity to their observed brightness, astronomers measure distances across the universe. It was through such studies that scientists discovered the accelerating expansion of the cosmos, evidence of what we now call dark energy. And so, The death of stars becomes a window into the universe itself. From the ashes of collapse, we learn not only about matter and life, but about space, time, and the fate of all things. When we stand beneath the stars at night, it is easy to forget that some of them are already in the final stages of life. Some may explode tomorrow, others in 1,000 years, others in 1,000,000. The universe is vast and its timescales are slow compared to ours, but every point of light carries within it the seeds of transformation. Betelgeuse will one day join that story. Its final explosion will scatter its elements into space. Perhaps millions of years from now, those elements will form a new star, a new planet, maybe even life that looks up at its own night sky in wonder. The stars remind us that endings and beginnings are not separate. They are bound together, two sides of the same cosmic rhythm. The end of a star's life may sound like destruction, but in truth, it is also creation. Every supernova is both an ending and a gift, scattering elements that shape future worlds. This is why astronomers sometimes call them the great recyclers of the cosmos. Take our own planet. The iron in Earth's core, the oxygen in our lungs, the calcium in our bones, all were once forged in stars. Long before the sun was born, earlier generations of massive stars lived, died, and exploded, spreading their enriched material across the galaxy. When a cloud of gas and dust eventually collapsed to form the sun and its planets, those elements were already present, woven into the very matter that would become Earth. This cycle is ongoing. Today, stars are still being born in vast nebulae, clouds shaped by earlier explosions. Some of the most beautiful regions in the sky, such as the Orion Nebula, glow with the energy of new stars igniting within. If we could watch over millions of years, we would see the same story repeating: birth, life, death, renewal. Supernovae also leave behind striking remnants, each telling its own story. The Veil Nebula in Cygnus, with its delicate threads of glowing gas, is the aftermath of a star that exploded thousands of years ago. The Cassiopeia, a remnant, reveals layers of elements cast into space, still expanding centuries after the explosion. Each remnant is like an open book, its filaments tracing the last breath of a star. At the centre of some remnants lie neutron stars, dense, spinning cores left behind after collapse. In others, the collapse is so complete that a black hole remains, invisible except through its influence. These remnants are not passive. They shape their surroundings, stirring gas, igniting shock waves, and altering the environments where new stars will one day form. It is a humbling thought. The night sky is not fixed, though it appears so to us. Behind its calm beauty lies ceaseless change. Stars are born, they grow old, they die, and their ashes give rise to new generations. It is a rhythm far slower than human life, but more enduring than any civilization. When we look at Betelgeuse, or any other bright star, we are seeing a moment in this long cycle. To us, it is a familiar presence in winter skies. To the universe, it is simply one more chapter in an endless sequence of birth and renewal. This cycle, patient and steady, is what makes the cosmos alive. Without it, galaxies would fade, planets would never form, and life would have no raw materials to build upon. In the quiet of night, we can sense this truth, that our existence is tied to stars and to their deaths. Perhaps this is why supernovae hold such fascination. They are both a reminder of impermanence and a reassurance of continuity. In their light, fleeting yet powerful, we glimpse both our fragility and our belonging. As we move deeper into this story of stellar endings, we begin to see how the universe balances violence with creation. The explosions of stars may seem chaotic, but they follow a quiet necessity. Without them, the cosmos would be empty of the diversity we know. With them, there is renewal, galaxies enriched, new generations of stars prepared, and the elements of life scattered like seeds into fertile ground. Astronomers study these events not only for their beauty but for their lessons. A supernova is like a natural laboratory, offering conditions far beyond what we can reproduce on Earth. Within its core, pressures and temperatures rise to unimaginable extremes. For moments, matter behaves in ways that stretch our models of physics. By observing these explosions across radio waves, visible light, X-rays, and gamma rays, we test the boundaries of our understanding. Even today, we do not fully know how every detail unfolds. Why do some stars leave behind neutron stars, while others collapse into black holes? What shapes the strength of their explosions? What decides whether a dying star produces a gamma-ray burst? These questions remain open, inviting patient exploration. The tools we use to seek answers are themselves remarkable. The James Webb Space Telescope peers into the fading light of ancient supernova, measuring the faint glow of elements newly formed. Ground-based observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii capture spectra that reveal the chemical fingerprints of these stellar deaths. Together they allow us to trace the story written in starlight, and sometimes these studies bring us close to our own place in the universe. In 1987, a supernova lit up the sky of the southern hemisphere. Known as Supernova 1987A, it was the closest observed in modern times in a neighbouring galaxy called the Large Magellanic Cloud. For months, it shone visibly without telescopes. For the first time, scientists detected neutrinos, ghostly particles released in the explosion, offering direct evidence of what happens deep inside a collapsing star. That event was more than a discovery. For many who saw it with their own eyes, it was a moment of awe, a reminder that the universe is alive with change. People stepped out into the night, looked upward, and witnessed the death of a star, its light carrying across 160,000 years to reach Earth. Supernovae are rare in any single galaxy, perhaps one every 100 years in the Milky Way. But across the billions of galaxies in the universe, they happen constantly. Somewhere at this very moment, a star is collapsing, its light just beginning a journey that may take millions of years before arriving at some distant world. It is a quiet thought, that the universe is always changing, even when the sky above us seems still. Every star holds within it a future, every galaxy a rhythm of birth and death. We are part of that rhythm, shaped by it, sustained by it. And so, as we reflect on these vast cycles, we can carry with us a simple awareness that to exist is to be connected through time and matter to the stars themselves. If supernovae show us the spectacular endings of stars, then their remnants remind us that nothing in the universe is wasted. The clouds of gas and dust left behind drift outward, cooling and reshaping. Over time, they mix with surrounding interstellar material, enriching it with heavy elements. These enriched regions become the nurseries where new stars are born. The Crab Nebula is perhaps the most famous example. Nearly 1,000 years ago, in 1054 CE, Chinese and Middle Eastern astronomers recorded a new star that appeared suddenly in the sky. It was so bright that it was visible even in daylight. Today, telescopes reveal the nebula it left behind, a tangled web of glowing filaments, still expanding, still carrying the energy of the star's death. At its heart spins a pulsar, a neutron star rotating dozens of times each second, sending beams of radiation like a cosmic lighthouse. Other remnants tell similar stories. The Veil Nebula shows delicate curtains of gas like coloured threads stretched across the sky. The Cassiopeia A remnant glows in X-rays, its gas is still hot, revealing layers of elements that were once locked inside a star. Each one is a snapshot of transformation, a reminder that death in the cosmos is never final. But these remnants are not only beautiful, they're also active agents in shaping galaxies. Their shockwaves compress nearby gas, triggering the birth of new stars. Their elements combine into dust grains that may one day form planets. Even here, in our solar system, the iron in Earth's core, the oxygen we breathe, the calcium in our bones, all of it was forged in the furnaces of stars that exploded long before the sun was born. This knowledge changes how we look at ourselves. To say that we are made of stardust is not a metaphor, it is literal. The atoms that form our bodies were assembled in ancient stars, carried across light years, and gathered into the cloud that became our solar system. In this sense, each of us is a continuation of stellar cycles, a living echo of explosions that happened billions of years ago. And these cycles continue. Even now, somewhere in the Milky Way, a star is reaching the end of its life. Perhaps in the distant future, another supernova will enrich our galaxy once more, scattering its elements to prepare the way for stars and worlds yet unborn. It is easy to think of the night sky as permanent, but the truth is, it is alive with change. Stars come and go. Galaxies collide and reshape. Even black holes, seemingly eternal, evolve over unimaginable spans of time. Nothing is fixed, and yet everything is connected. The remnants of supernovae remind us of this continuity. They are not just ashes, they are beginnings. They are chapters in the long story of the universe, written in light, gas, and time. So when you look up and see Orion, or Cassiopeia, or Cygnus, know that behind those patterns of stars lie histories of fire, collapse, and renewal. The quiet night sky is not quiet at all. It is the surface of a story still unfolding. The study of supernova also opens a window into the very fabric of the universe. Some types, like Type Ia supernova, are so consistent in brightness that astronomers use them as standard candles to measure cosmic distances. By comparing their known luminosity to how bright they appear from Earth, scientists can calculate how far away they are. It was through the careful study of these explosions that, in the late 20th century, researchers discovered something astonishing. The universe is not only expanding, but its expansion is accelerating. This revelation led to the concept of dark energy, a mysterious force that seems to push galaxies apart. Without Type Ia supernovae, this profound truth might have remained hidden. So, in a sense, the death of stars helped us uncover one of the greatest mysteries of existence. From their light, we learned not just about galaxies, but about the ultimate fate of the cosmos. Will expansion continue forever, leaving galaxies isolated in darkness? Will dark energy change, causing the universe to slow or even collapse? These are questions still unanswered, carried within the faint glow of distant supernovae. But beyond cosmology, there is another layer of wonder. When a star explodes, it is not only a physical event, it is also a cultural one. Human beings across history have watched these sudden lights in the sky with awe. Ancient records from China, Japan, the Middle East and Europe describe guest stars appearing where none had been before. Some were seen as omens, signs from the heavens. Others were incorporated into myths or religious beliefs. Today, though we know the science behind them, the awe remains. The difference is that we can now connect that awe to understanding. We can point telescopes, record spectra, and model the physics of collapse. But even as we do, we are still the same creatures who once looked up in wonder, asking what these lights meant. That continuity, between ancient sky watchers and modern astronomers, reminds us of something profound. Knowledge changes, but wonder endures. Whether we see a new star as divine sign or as a collapsing giant, the feeling it awakens in us is the same. Humility before the vastness of the universe, and in that humility there is peace. The stars remind us that our lives are brief compared to theirs, yet connected to them in every atom. They remind us that endings can be beginnings, and that even destruction has beauty when seen in the context of time. Perhaps this is why so many find comfort in astronomy. To know that the stars are born, live and die as we do, but on a far greater scale helps us feel less alone. To know that their death seeded the elements that make up our bodies ties us directly to the cosmos. We are not separate, we are participants in its rhythm. So the next time you step outside and see the night sky scattered with light, remember this: those points of light are not eternal. They are lives in progress, some just beginning, some near their end, each one part of a cycle older and grander than anything on Earth. When we speak of the universe as a cycle of birth and death, perhaps no process embodies this more clearly than the life cycle of stars. Each stage flows into the next, bound by the quiet laws of physics, unfolding across timescales so vast that human history seems like a fleeting moment in comparison. Stars begin in clouds of dust and gas known as nebulae. Gravity gathers this material, pulling it tighter until heat and pressure ignite nuclear fusion. A new star is born, glowing steadily, balancing the inward pull of gravity with the outward push of fusion. For most of its life, a star remains stable in this main sequence, quietly shining, but nothing lasts forever. In time, hydrogen runs low, fusion shifts, and stars change. Small stars fade gently into white dwarfs. Massive stars swell into giants, then collapse in explosions. Their deaths scatter elements into space, seeding future generations. These cycles overlap. The death of one star feeds the birth of another. The Milky Way itself is full of such rhythms, with star-forming regions glowing where old material has been recycled into new light. The Orion Nebula, visible even to the naked eye as a smudge below Orion's belt, is one such nursery, a place where newborn stars still ignite, surrounded by the remnants of earlier ones. On Earth, we see only a sliver of this vast process. A single human lifetime is not long enough to witness a star's full arc. Yet through telescopes, by observing different stars at different stages, astronomers piece together the story as though flipping through the pages of a book too large to read in one sitting. And through this story, we come to see our own place. The carbon in our cells, the oxygen in our breath, the iron in our blood, each was created in a star long before the sun was born. We are not only observers of the cosmic cycle, we are participants, built from it, carried by it, and one day, we too will return to it. There is something calming in this thought. It means that nothing is wasted, that even in endings there is continuation, that the universe, in its quiet patience, makes use of everything. And so, when you look up at the sky tonight, remember that the light reaching your eyes has travelled for hundreds, thousands, even millions of years. Some of those stars may already have died, their light still crossing space. Others are just beginning their lives. Together they weave a tapestry of time and change, a reminder that the cosmos is alive, not static. This perspective can be grounding. Our daily concerns feel heavy in the moment, but compared to the cycles of stars, they are light, brief, and passing. The stars remind us to breathe, to slow down, to accept that change is natural. They remind us that endings can be beginnings, and that nothing in the universe is ever truly lost. There is another mystery woven into the story of stellar death, one that brings us back to the most powerful explosions of all, gamma-ray bursts. These fleeting flashes, lasting mere seconds or minutes, are so intense that they can outshine entire galaxies. For astronomers, they are like sudden whispers from the farthest reaches of the cosmos, bright, brief, and full of meaning. Yet their origins are complex. Some gamma-ray bursts are linked to the collapse of massive stars, stars many times heavier than our Sun. When such a star collapses into a black hole, its rotation and magnetic fields can funnel energy into narrow jets. If one of those jets happens to align with Earth, we detect a gamma-ray burst. Others come not from single stars, but from collisions, two neutron stars spiraling together, merging in a flash of light and gravitational waves. In either case, the bursts are a final act of transformation. They are the universe at its most extreme, bending the laws of physics to their limits, and in their violence they also give rise to new matter. In some bursts, astronomers believe the heaviest elements, gold, platinum, uranium, are forged. The jewellery on a hand, the circuits in a computer, even the radioactive decay that warms Earth's interior may trace their origin back to these rare explosions. In 2017, the collision of two neutron stars was detected not only through light, but through gravitational waves, ripples in space-time itself. For the first time, humanity observed the same event in two ways, through the trembling of light and the trembling of space. The discovery confirmed decades of theory and showed us that even the most catastrophic events could be sources of creation. Yet much about gamma-ray bursts remains uncertain. Why are some so much brighter than others? Why do their afterglows sometimes reveal heavy elements and sometimes not? Are there types of bursts we have yet to recognize? The universe gives us clues, but rarely full answers. There is comfort in this uncertainty. Science does not seek to finish the story, but to deepen it. Each burst we observe is another chapter, another chance to refine our questions. Each detection is a reminder that discovery is not a sudden revelation, but a slow unfolding, just like the universe itself. And perhaps that is why gamma-ray bursts, though rare and fleeting, feel so meaningful. They are like cosmic echoes, telling us that creation and destruction are never separate, that even the brightest, briefest flash can shape the course of galaxies and the matter that builds our world. Somewhere, right now, another burst may be unfolding. Its light is on its way to us, crossing millions or billions of light years. One day it will reach our instruments, carrying with it a new piece of the puzzle. If gamma-ray bursts show us the sudden violence of the universe, then the quiet persistence of starlight shows us its gentler side. Between the extremes of birth and death, stars spend most of their existence in steady balance. This balance is what allows galaxies to shine, what allows planets to orbit, and what allows life to emerge. Our own sun is a perfect example of this equilibrium. For billions of years it has fused hydrogen into helium at its core, releasing light and heat at a constant rate. That light sustains life on Earth, warms our oceans, drives our weather, and powers the growth of plants. It is easy to take for granted, but in truth, it is extraordinary. A perfect balance between collapse and expansion, maintained across vast spans of time. But the Sun, too, is part of the larger cycle. In about 5 billion years, it will exhaust its hydrogen. It will swell into a red giant, engulfing the inner planets, perhaps even Earth. Then, as its outer layers drift into space, it will leave behind a white dwarf, a dense, cooling remnant that will shine faintly for trillions of years. Though gentler than a supernova, this ending carries the same theme: renewal. The material shed by the Sun will enrich the interstellar medium, contributing to future generations of stars and planets. Even the calmest of endings has purpose. The contrast between stars like the Sun and giants like Betelgeuse reminds us of the diversity of cosmic lives. Some stars die quietly, others in explosions visible across galaxies. Yet all follow the same rules of physics, shaped by mass, pressure, and time. Their variety gives texture to the universe, ensuring that not every galaxy looks the same, not every system evolves in the same way. And beyond the deaths of individual stars, there are larger dances at play. Galaxies themselves are not static. They collide, merge, and reshape. When two galaxies meet, their stars mostly pass by one another, separated by immense distances. But their gas clouds interact, compressing, sparking waves of new star formation. At the centers of those galaxies, their supermassive black holes spiral toward one another, eventually merging in cosmic unions that release titanic amounts of energy. We live in such a universe of motion. The Milky Way itself is destined to merge with the Andromeda Galaxy in about 4 billion years. From Earth's perspective, if humanity or its descendants are still here, the night sky will fill with the glow of Andromeda drawing closer, its spiral arms stretching across the heavens. What seems today like two separate galaxies will become one, reshaping the stars, gas, and black holes within. Even on the grandest scales, then, the theme is the same. Endings and beginnings blur. A star's death gives birth to new stars. A galaxy's collision sparks new generations of light. Nothing is wasted, nothing is final, everything is transformation. When we look up at the night sky, we see only the stillness of stars. But in truth, every point of light is part of an ongoing story, a story of balance, collapse, renewal, and connection. As we follow this thread of cosmic change, it becomes clear that the universe is not a static place at all. It is dynamic, restless, always in motion. Even when we see the still night sky, what we are really observing is a frozen frame of processes unfolding across millions and billions of years. Take, for instance, the stars of the Milky Way. They orbit the galactic centre in great spirals, like dancers moving slowly around a stage. Our own Sun takes about 225 million years to complete one orbit. That means in all of Earth's history, since the age of the dinosaurs, the Sun has circled the galaxy only a handful of times, and galaxies themselves are not fixed either. They drift, drawn together by gravity, colliding and merging in great cosmic events. The collision of the Milky Way with Andromeda will not be an act of destruction, but of transformation. The shapes of both galaxies will warp, their stars redistributed, their black holes eventually coalescing. For beings alive then, if any exist, the night sky will look unimaginably different, filled with streams of stars stretching across the horizon. The universe, in this way, shows us two truths at once. On human timescales, it feels stable and enduring, but on cosmic timescales, it is ever-changing, fluid, alive with movement. The same applies to the smallest scales we know. Within atoms, particles flicker in and out of existence, guided by quantum rules. The same laws that govern the fall of stars also guide the behaviour of the tiniest building blocks of matter. From galaxies to quarks, the pattern repeats, a universe in motion, governed by balance, always seeking transformation. And at every level there is a common rhythm, collapse and expansion, order and entropy, birth and death. It is this rhythm that binds us to the cosmos. We are not apart from it. We are shaped by it, carried within it, made of its dust and energy. Even the idea of permanence becomes different under this view. The atoms in our bodies will not stay as they are forever. Long after our lives end, they will disperse, recycled into new forms. Some may return to the soil, some may drift into the atmosphere, and some, carried far by time, may even find themselves part of a star or a planet in the far future. There is a quiet comfort in this. Nothing is lost. Everything continues, in another form in another time. The stars remind us that our own endings are not final either. They are transitions, small echoes of the same processes that shape galaxies. So when you look at the sky tonight, perhaps you will see not just points of light, but a story of change unfolding, slowly and steadily, all around us. A story in which we too are participants. If we let our thoughts linger on this idea of continuity, another question emerges: what then is the ultimate fate of the universe itself? Just as stars live and die, and galaxies merge and change, could the cosmos itself also have a life cycle? Astronomers have long pondered this. The evidence shows that the universe is expanding, galaxies rushing away from one another like embers carried on the wind. For a long time, scientists assumed gravity would eventually slow this expansion. Perhaps it would stop. Perhaps, in time, everything would collapse again in a big crunch. But the discovery of dark energy changed that picture. In the late 1990s, by studying distant Type Ia supernovae, astronomers realized that the expansion of the universe is not slowing, it is speeding up. Something unseen, something woven into the very fabric of space, is driving galaxies apart faster and faster. If this acceleration continues, the universe's future will be one of separation. Galaxies will drift farther from each other, until eventually distant ones will fade from view entirely, carried beyond the limits of what light can reach us. In trillions of years, the night sky may grow dark, not because stars have gone, but because their light can no longer find its way here. On smaller scales, stars will still live and die. Supernovae will still scatter elements, but over longer stretches, new star formation will slow as gas is consumed. White dwarfs will cool, neutron stars will fade, black holes will dominate, and even those black holes, according to Stephen Hawking's theory of Hawking radiation, will not last forever. Slowly, over timescales so vast they defy comprehension, they too will evaporate, leaving only thin radiation behind. This vision is sometimes called the heat death of the universe, a future where everything is spread thin, no new stars are born, and the cosmos becomes quiet, cold and dark. It is a picture not of sudden collapse, but of slow fading, like the last embers of a fire. Yet even this ending, if we can call it that, carries the same theme as all others. It is not a destruction but a transformation. The energy, the matter, the structures we know may change beyond recognition, but they will not vanish. The universe will continue, in a different form, as it always has. And perhaps this is the deeper message the cosmos offers us, that change is not to be feared. Stars explode, galaxies collide, universes expand, and still something endures. Patterns shift, but nothing is truly lost. For us, living on a small planet orbiting a modest star, these timescales are almost beyond imagination, yet they remind us of something simple, that our lives, brief as they are part of this same story, that we exist not apart from the universe, but within it, shaped by its cycles, carried forward by its transformations. So when you look at the night sky, know this: you are not just watching the universe, you are the universe, watching itself. The thought of the universe watching itself through us is both humbling and calming. We are small, yes, but not insignificant. We are expressions of the cosmos, made of its elements, shaped by its rhythms, carried by its time. Consider again the atoms that form your body. The oxygen you breathe was forged in stars that lived and died billions of years ago. The calcium in your bones was once part of an exploding giant. The iron in your blood was created in the core of a star that collapsed long before the Earth existed. Each breath, each heartbeat, is a quiet continuation of cosmic history. This connection is not poetic invention, it is science. The periodic table itself is a record of stellar processes. Hydrogen and helium emerge from the Big Bang. Carbon, oxygen, nitrogen, and silicon came from fusion inside stars. Heavier elements like gold and uranium required the extraordinary conditions of supernovae or neutron star collisions. To trace the elements is to trace the story of the universe itself. When we look at the sky then, we are not separate from it. The stars are not out there, and we, down here. We are part of the same unfolding. The cosmos is not something we visit with telescopes. It is something we already belong to, and perhaps that is why the night sky has always stirred human beings. Long before telescopes, long before science, our ancestors looked upward and felt awe. They told stories about the stars, shaped myths and constellations, and found guidance in their patterns. Without knowing the physics, they sensed the truth, that the stars mattered, that they were part of our story. Today, we know more of the details. We know about nuclear fusion, gravitational collapse and black holes. We can measure distances in light years, trace the lives of galaxies, and model the future of the universe. Yet the feeling is unchanged. The knowledge deepens the wonder. It is this blend of understanding and awe that makes astronomy unique. To learn about the universe is not to reduce its mystery, but to expand it. Each answer leads to new questions, each discovery to new horizons. The cosmos is not diminished by our knowledge, it is enriched, and in a quiet way, it enriches us too. To know that we are made of stardust, to know that our lives are woven into cycles of birth and death on scales beyond imagination, can bring perspective. It can make our worries feel smaller, our moments of joy feel more precious, our lives feel connected to something vast and enduring. So let us pause with this thought. The universe is not cold or distant. It is within us. It lives in our cells, our thoughts, our breath. To study it is to study ourselves. As we carry this perspective forward, it helps to remember that our study of the cosmos is still in its early stages. We have only recently begun to glimpse black holes directly, only recently detected gravitational waves, only recently measured the faint afterglows of the first stars. The universe is vast, and our understanding of it is still like the first few lines of a book. Yet even these early pages have revealed patterns of astonishing depth. We see that the same physical laws apply everywhere. The light from distant galaxies obeys the same rules as the light in our laboratories. The atoms in stars behave as they do on Earth. The mathematics of gravity bends both the fall of an apple and the path of a planet around its star. This unity of law is what allows us to understand the universe at all. It means that when we look across billions of light years, we're not looking into something foreign, but into an extended version of the world we already inhabit. The cosmos is not strange, it is familiar, expanded, and this familiarity allows us to feel at home within it. Though the scales are vast, the patterns are continuous. Our bodies, our world, our stars. They are not exceptions, but examples. To see this is to find comfort, that we are not accidents adrift in chaos, but expressions of a larger order. The more we learn, the more we see that change itself is the constant. Stars are born and die. Galaxies collide and merge. Black holes grow, fade, and may even evaporate. Even space itself expands, carrying galaxies farther and farther apart. Change is not something that happens to the universe, it is what the universe is. And yet, within this constant motion, there is peace. The rhythms are slow, the cycles vast, the transformations patient. To compare our brief human lifetimes with the long lives of stars is not to diminish us, but to remind us that we are part of a story larger than we can live to see. We play our part and then the story continues. Perhaps this is why so many people find astronomy restful. To listen to the quiet truth of the cosmos is to feel perspective. Our struggles and worries, though real, become smaller against the backdrop of galaxies. Our joys, though fleeting, become more precious because of the brevity of our time. So when you look up at the stars, you're not only seeing points of light, you're seeing the flow of time, the persistence of change, the memory of creation. You're seeing the same patterns that shape your own body, your own life. It is a reminder, simple and gentle. We belong to the universe, and the universe belongs to us. The belonging we feel when we look at the stars is not an illusion. It is written in physics, in chemistry, in the structure of matter itself. We are bound to the universe not just by imagination, but by substance. Think of the air you breathe. The oxygen within it was formed in the fusion cores of ancient stars, carried across light years before settling into the clouds that birthed our solar system. Think of the water in your body. The hydrogen it contains has been present since the very first moments after the Big Bang, unchanged for nearly 14 billion years. Each sip, each breath, carries the weight of cosmic history. When scientists study starlight, they are not only studying distant suns. They're also reading a universal record, a kind of archive of time. Every atom and photon holds a story. Light stretched by the expansion of the universe tells us how space itself evolves. The patterns in spectral lines reveal the elements forged long ago. Even the faintest cosmic microwave background, a whisper of radiation left from the Big Bang, carries the memory of the universe's birth. And as we learn to read these signals, we see more than facts. We see connections. The same physics that governs a collapsing star also governs the chemical bonds in our cells. The same mathematics that describes galaxies describes the orbit of Earth around the Sun. The universe is not separate systems, but one whole, a continuity that extends from the largest clusters of galaxies to the smallest living beings. This awareness can feel almost like a deep breath, a reminder to slow down, to notice that we are part of something steady, something older and greater than ourselves. For all its violence, its explosions, its collisions, its collapses, the universe also shows patience. Stars live for billions of years. Black holes linger across timescales so vast we cannot imagine them. Even galaxies, restless though they are, take billions of years to merge and change. In comparison, our lives are brief. But they are not meaningless. They are one thread in this fabric, one expression of matter and energy that has been assembling itself since the beginning. To live is to participate in the story of the cosmos. So the next time you see the night sky, let it be more than distant points of light. Let it be a mirror. The universe is not only above you, it is within you, in every atom, in every breath. To rest beneath the stars is to rest within the very structure of existence. The more deeply we reflect on this, the more the night sky becomes not only an object of study but a companion. Its light, steady and patient, has been with humanity since our beginnings. Before cities, before writing, before history itself, people gathered under the same stars, watching their slow movements, finding patterns and telling stories. Those stories varied from culture to culture: heroes, hunters, animals, spirits. But the act was the same everywhere. Human beings looked upward and sought meaning. The constellations became a canvas for imagination, a way to connect human life with the vastness above. Even without telescopes, even without science, our ancestors sensed what we know today, that the stars matter, that they are part of our story. In time, curiosity deepened. Observers began to measure the stars' positions, noticing cycles and predicting their returns. From these efforts grew calendars, navigation, and the beginnings of astronomy. The stars guided travellers across seas, helped farmers know when to plant, and inspired philosophers to wonder about the structure of the universe. Now, with our modern instruments, we see far more than our ancestors could have dreamed. We have mapped galaxies billions of light years away. We have detected the faint signals of the universe's earliest moments. We have sent spacecraft beyond our solar system, carrying with them tiny records of who we are. And yet, the feeling is still the same, a mixture of curiosity, humility, and wonder. Science and story are not separate here. They are layers of the same human response. The constellations gave us meaning when knowledge was scarce. Astronomy gives us meaning now, through the quiet assurance that we are part of something vast, lawful, and continuous. What makes this perspective soothing is not just its grandeur, but its patience. The universe unfolds slowly. Stars burn for millions or billions of years. Galaxies merge across spans of time longer than life on Earth has existed. Even the acceleration of the cosmos is measured not in days or centuries, but in eons. Against such scales, our hurried concerns lose some of their weight. This is not to diminish our lives, but to frame them. We are brief, but we are also connected. Our experiences are small, but they are real threads in the same cosmic fabric. To know this can be restful. It allows us to carry both the fleeting and the eternal at once. So perhaps the true gift of astronomy is not only knowledge, but perspective. The stars remind us of what endures, and they remind us of what is precious in our short time. Both truths coexist, quietly, in the same night sky. The sky, then, is both a teacher and a comfort. It shows us the mechanics of the cosmos, how stars are born, how they live, how they die, and it offers us perspective, reminding us of the scale and rhythm of existence. But it also holds something gentler, the ability to calm us, to quiet the mind, to remind us that we are part of something steady. When you gaze at the Milky Way on a clear night, what you're seeing is not just a band of stars. You're seeing the cross-section of our galaxy, hundreds of billions of suns spread across a disk, their light overlapping to form a misty glow. Each point is a story in progress. Some stars are just beginning to fuse hydrogen, others are near the end of their fuel, preparing to swell or collapse. Still others may have already died, their light continuing to travel toward us long after the star itself is gone. That thought can be strangely soothing, that the light reaching your eyes tonight began its journey thousands, even millions of years ago. It means that the stars carry with them a memory of the past, and that by simply looking upward you are seeing across time. This time travel of starlight connects us not only to distant suns, but also to the people who lived before us. The same stars we see now were seen by those who built the pyramids, who crossed oceans, who told stories by firelight. The constellations are like shared memory, linking all of human history to the same sky. And as science expands that memory, we learn to see more. Telescopes capture wavelengths beyond our eyes, infrared, ultraviolet, X-rays, revealing galaxies, nebulae, and black holes. What once looked like empty space is alive with hidden structures, vast and delicate, waiting to be revealed. Yet even with all this knowledge, the sky keeps its calm. It does not rush. Galaxies turn slowly. Stars burn at their steady pace. Black holes gather material in silence. The universe is patient, and it invites us to share in that patience. Perhaps this is why astronomy lends itself so well to rest. To listen to the story of stars is to let go of urgency. To follow the cycles of galaxies is to breathe more slowly, to remember that time stretches far beyond our worries. In this way, science becomes not only explanation, but meditation. Each fact is a reminder of continuity. Each discovery is another way of saying, the universe goes on, and so do we, in one form or another. So as you listen, as you imagine the stars above, let them remind you. Change is natural, endings are beginnings, and nothing is truly lost. The cosmos continues gently, patiently, endlessly. If we follow this rhythm of patience even further, we begin to see the cosmos as a great unfolding tapestry. Each thread is a star, a galaxy, a molecule, or even a single atom. Some threads are bright, woven into dazzling patterns of light. Others are quiet, almost invisible, yet no less important. Together they create a fabric that stretches across space and time. Within that tapestry, our own solar system is just a small motif. The sun burns steadily, carrying Earth and the other planets in its orbit. Around us, comets sweep long elliptical paths, asteroids drift, and moons turn like watchful companions. All of it feels familiar, yet all of it is temporary. The solar system itself is only a chapter in the galaxy's longer story. Still, this chapter is precious to us. Earth, with its thin atmosphere and oceans of water, is a rare place where life has taken root. And life, through billions of years, has changed and grown, from simple cells to vast forests, to creatures that now look up at the stars and ask questions. That too is part of the cycle. The universe not only produces stars and galaxies, but eventually observers, beings capable of reflection, of wonder. It is worth pausing on that thought. The atoms that once swirled in the heart of ancient stars are now the same atoms that form your mind. Through you, the universe has gained the ability to think about itself. When you reflect on starlight, the cosmos is reflecting too. Astronomers often say that to look at distant galaxies is to look back in time. Their light has travelled for millions or billions of years to reach us. In the same way, to look inward, to the molecules of life, to the structure of DNA, is also to look back, to see the record of countless generations of stars and elements that came before. Both directions, outward and inward, lead us into history, into origins. And in both directions, the lesson is the same: continuity. Nothing is separate. The galaxies above and the cells within are chapters of the same story. Different scales, different rhythms, but one process, one universe. This realization can bring calm, for if we are part of a story so vast, then our smallness is not a flaw, it is a feature. We are meant to be small, just as a note is small in a song, or a thread is small in a fabric. Yet without those notes, without those threads, the whole would not be complete. So tonight, if you find yourself beneath the stars, let them remind you of this. You're not apart from the cosmos. You're not an outsider looking in. You're a participant, a continuation, a necessary thread in the fabric of existence. As we drift further into this reflection, it becomes clear that the universe speaks in cycles, and that we are always within them. From the smallest atom to the largest cluster of galaxies, everything flows in patterns of transformation. Think of water on Earth. It evaporates from oceans, forms clouds, falls again as rain, and returns to rivers and seas. It changes form, but it never disappears. Now lift that image to the stars. Hydrogen gathers in clouds, collapses into fusion, shines as light, and eventually scatters into heavier elements. Those elements drift, join new clouds, and form new stars. The pattern is the same: movement, transformation, continuation. Even black holes, often thought of as the universe's endpoints, are part of this flow. Though their gravity is immense, though nothing that crosses their event horizon can return, they too evolve. Over unimaginable timescales, They may slowly lose energy through Hawking radiation, fading away like embers. Even the most absolute-seeming structures are not eternal. They too are woven into the rhythm of change. For us, these timescales are nearly impossible to grasp. Our lives are measured in decades, civilizations last centuries, perhaps millennia. Stars, galaxies, and black holes stretch into billions and trillions of years. Yet the fact that we can even imagine such scales is remarkable. It shows that consciousness, however brief, has the ability to reach far beyond its own span. And this reaching is not only intellectual, it is emotional. We feel something when we look at the stars, something quiet and grounding. It is as though the vastness above us has the power to place our worries in perspective, to remind us that life moves on and that we are part of something steady. That is why astronomy is not only science but also comfort. To know that the universe has endured for billions of years before us and will endure for billions after is to feel held by a larger continuity. It does not diminish our lives, it frames them. It shows us that our moments, though small, are not isolated. They are connected, stitched into the same